What's that?
I raised my hand to do that.
Okay, take a moment, get yourself organized, get your binders or your whatsy-woos together, and then once you've got it together, we are on page 5. Page 5. Hi.
I don't think I got my first half.
Oh, the first half? Yeah.
Yeah. Yeah.
I wake up next day, like birthday bake. Sleep over the week, but
Yeah. It's a video to watch with Tyler DeWitt.
Okay, if it's yeah, sure. Then yeah.
Okay. Oxidation numbers, which we talked about yesterday, are, if you recall, they are kind of like a charge. So they're kind of like a charge. So if you have Na and there is nothing at the top, what is the charge? It's 0, so the oxidation number therefore is 0. In fact, the oxidation number of any lone element is 0. Do you guys know what I mean by a lone element? An element on its own, not paired up with anybody else in a compound. I do not mean sodium plus, because sodium plus would be part of a compound, maybe NaCl or NaNO3 or Na2CO3 or any number of things. But Na plus would be part of a compound. So that is not a lone element. And you just, when it's a metal, you just go with its charge. Okay, so you go, what is the charge of sodium? It is +1. And so the oxidation number is +1. What is the charge of O in Na2O? It's just normal oxygen. Yes. 2-. Most of my grade 9s could tell me that. Yes, I'm not asking for anything weird here. This is just normal. Okay, so don't get trying to think too fancy. This is very basic, normal stuff. Okay, O is -2. And in fact, almost all the time, O is going to be -2. It's one of the ones that we usually know. Okay. Now, there are compounds and ions. We can find them for atoms that are bonded covalently and do not have charges. Okay, but they are useful for determining whether something has been oxidized or whether it has been reduced. So for example, you could find the oxidation number of C in C2O4 2- is +3. And today we will learn how to calculate that, okay? The oxidation number of carbon in C3H8 is actually -8/3. Which brings us to another point, and that is that oxidation numbers can be fractions. And again, you will learn how to calculate that. Yes. Isn't what? So we have O4. Here's how we're going to do it, okay? This is just a preview of the technique. We're going to say I have 2 carbons, I have 4 oxygens, and my net charge is -2. So I have 2 carbons that I don't know the charge of. I have 4 times -2 because oxygen is -2, and my net charge is -2. So I have 2 carbons minus 8 equals -2, and so I have 2 carbons is equal to +6. So carbon is equal to +6 over 2, which is equal to +3. Did you follow that? Yeah? So that's how we figure them out. Okay, and we're going to do a bunch of practice. Okay, but that's just a quick showing how to do it. Yeah? Because we had 2 carbons, we have 4 oxygens, and those 2 carbons and 4 oxygens together give us a charge of -2. We know the charge of oxygen is 2-. It is one of the ones where we know the oxidation number. Carbon is one of the ones where it has very differing oxidation numbers depending on who it's with. So we're going to figure it out based on the fact that we have oxygen attached to it and a -2 charge. Yes?
Why is oxygen going to the non-carbon?
Because oxygen is the thing that does the oxidizing usually. Okay? And there are certain things that are just constant, like all your alkali metals. Have you ever known an alkali metal to have anything other than a +1 charge? No, therefore all alkali metals have a charge of +1. They all have an oxidation number of +1. How about group 2 metals, alkaline earths? +2, so they have an oxidation number of +2. So when you have an oxidation number, a couple things I just wanted to make sure you know before we start going crazy on them. They can be fractions, and they must include the positive or negative sign, except if you have 0. So if it is positive, you must write positive. You can't just write 6. If it's +6, it's +6, okay? Because you need to show me which direction it's going. It's just a convention, okay? So here are the rules that we'll base it on. We've already gone through the first few. Any lone element has an oxidation number of 0. Alkali metals. Oh, guess what? You just told me this one. They always have an oxidation number of 1 unless they are a lone metal. Yeah, right? This is when they're in compounds. So this first one is in pure elements. Lone elements are 0. But if we're in compounds, then rules 2 through whatever are the ones we follow. Alkaline earth metals always have an oxidation number of +2. And you'll notice we have always and always. There are no exceptions. Hydrogen, and these rules go in priority of like highest always value. You know what I mean? Like, so we go with always, always, and then we go with hydrogen, which has one exception. And hydrogen is normally +1. But there is one exception. And we'll come to that in a moment. The reason I'm not showing you the exception right now is that I've found when I show the exception right away, people start looking for the exception everywhere. They're like, oh, it must be a hydrogen. Oh my goodness. Is hydrogen -1 here? They get all excited by the exception, and then they forget that all like 95 to 98% of the time, it's going to be +1. So don't go looking for zebras when it's just horses, you know? All right. What's that? Okay. Oxygen. Oxygen has an oxidation number of -2. And again, there is one exception. Halogens have an oxidation number of -1. Now, fluorine is always. Fluorine doesn't have an option. Why doesn't fluorine have an option? Yes? It does not have an empty D subshell, okay? Because it is row 2, there is no 2D subshell, okay? You don't need to be able to explain that, but... However, chlorine, bromine, and iodine may have many exceptions. But once again, may have, if you're trying to find something else, like if you're asked to find carbon's oxidation number, you can assume that chlorine is -1. Yes? If you're finding sulfur's oxidation number, you can assume that oxygen is going to be -2. You can assume, unless you're being asked to find the oxidation number of hydrogen or oxygen or the halogens, you can assume that they are +1, -2, and -1, because those are sort of the foundations upon which we build our other oxidation numbers. All right, so here's our exceptions. The exceptions. Hydride ions, H-, has an oxidation number of -1. And the peroxide ion, O2, 2-, has an oxidation number of -1. If you imagine you have an O attached to an O, and you've got -1 and you've got -1, that gives you -2 altogether, but each oxygen is only -1. Is good? Do you like how I put that on an angle so it didn't immediately appear rude? Clever, right? Never mind, it's all good. If you didn't notice, it's all good. You learned how to do things when you teach like molecules to grade 9s. Oh, we're going to draw oxygen vertically. Vertically is good. Okay. Occurs only when hydrogen, so here's our hydride. Hydride occurs only when hydrogen is paired with a metal, because metals are electron donors. Yes, they're always the ones that lose their electrons to become cations. And that would mean that hydrogen would be the electron acceptor. Is good? And in cases like this, we would say, what is the oxidation number of hydrogen in NaH? Well, you know that sodium is +1, therefore hydrogen must be -1. So that's the kind of place where you would find a hydride. When I ask you, what is the oxidation number of hydrogen in this compound? But if I was to ask you, what's the oxidation number of hydrogen in this compound? What would you say? +1, because chloride is -1 and hydrogen is +1. And we know that positive ions come first in compounds and negative ions go second, okay? Peroxides, you're going to look for an ionic compound or H2O2. An ionic compound or H2O2 that just looks a little weird. Does Na2O2 look normal? No. You're like, what? What? Why? Why are there 2 NAs and 2 O's? I don't get it. Okay. CaO2? Does that sound normal? No, because oxygen is -2 normally and calcium is +2. We should normally have CaO, right? And normally we have water, not H2O2. So this is hydrogen peroxide. Can you guess what this is? Sodium peroxide. People start looking for peroxides when we get into some organic compounds, but peroxide is an ion. It's never going to occur in, I guess, I don't know if I should, yeah, it's never going to occur in covalent or organic compounds. Yeah? Although all organic compounds are covalent. People get excited when they're like, oh, there's an O2 in this thing, but it's just an organic compound, and organic compounds have all kinds of O's all over the place. So we good? Okay. Once we know those rules, some of you will be able to do this in your head, and you will annoy me. Because I have to write it out so that I don't make dumb mistakes. Okay? So here's how we are going to do it. We are going to write out the number of each element. And then we're going to make it equal to the overall charge. So step number 1, if we have the example of NH4, we're going to write down the number of each element. And by the way, when we underline one, usually that's the one we want to find the oxidation number of, okay? How many nitrogens in this compound? 1 nitrogen. How many hydrogens? 4 hydrogens. How many chlorine? 1 chlorine. And we are trying to determine the oxidation number of nitrogen, which means we should know the oxidation number of hydrogen and of chlorine, okay? So we write down 1 nitrogen, 4 hydrogen, 1 chlorine. So we write the number of each element, and then we have it equal to the overall charge. What is the overall charge of this compound? 0. And this is where you need to remember your oxidation rules. Hydrogen is +1. We have 4 of those. Chlorine is -1. We have 4 of those. No, we have 1 of those. And nitrogen is the one we're finding, so we just leave it alone. Then we just do some algebra. You don't have to show like every step of the algebra along the way. When I'm showing an answer key, I will probably show more algebra than you would need to, but that way you can see exactly where I did the work, right? So if you make a mistake and forget to change something to negative, you'll be able to see where it happened. Okay, so we have 4 plus -1 gives us 3. So 1 nitrogen plus 3 equals 0. And then we bring 3 to the other side, which makes it negative. So the oxidation number of 1 nitrogen, and we always just want the oxidation number of 1, is -3. Is good? Is this less scary than it was yesterday when I just threw it at you as a preview? Yeah, right? Okay. CO3 2-. How many C's do we have? 1 carbon. How many O's do we have? 3 O's. And our overall charge is -2. So you write down 1 carbon, 3 oxygen equals the overall charge, which is -2. 2. Now, we're trying to find the oxidation number of carbon. So we're going to substitute oxygen as -2. 3 times -2 gives us -6. This stays the same. And then we move the -6 over to the other side and we get +4. So for the oxygen, or sorry, for the carbon, the oxidation number is -4. I kind of wish I'd made you like do these on your own. Do you want to cover it up and try it?
Yes.
Yes?
Yes.
Thank you. C3H2O2. Or you can just close your, you can just like put some paper over it and use this one here and be like, oh, look, that's the compound. We're finding the oxidation number of carbon. Yes? For now, just the reason I'm saying for now is that it gets harder and sometimes people mess up. And if you're messing up on the quiz, I want to know where you messed up. By the test, I won't care. On the quiz, I'd like to see your work. Did you guys get positive 2/3?
Yes.
Now, one thing is when you do get good at this, you can often just be like, you can be like, this is, you can be like, oh, this is +2, this is -4, and then you can be like, that's -2 equals 0 equals, I don't know. Like when it comes to fractions, I get a little lost in it, so I like to have it written out, but my tendency is if I don't write it out, I tend to put negatives where I shouldn't, or not put them where I should, or divide instead of multiply, or silly things. Okay, now let's see you get one like this. PB, what is the oxidation number of lead in PbNO3? Wait, just put your hand down, okay? And many people will look at this and they'll be like, oh my gosh, I don't know the oxidation number of nitrogen. How am I going to find this? That's okay, because what do you know? You know that nitrate is -1, yes? And you know that you have 2 of them, so you know your negative charge is -2. 2, so you know that lead is +2. So you're just going back to that stuff that you learned in grade 9, 10, 11, right? And you're saying, oh, I know how to find the oxidation number, the charge of a multivalent metal. I just use my negative ion and there it is, okay? But because we're doing oxidation numbers, sometimes people forget like that there's easy ways of doing that, right? It's like, oh, there should be some fancy new grade 12 way. Nope, it's just like before. Okay, there are some exercises here. I feel like we would be better spent. Oh, when you do the exercises, what I might do is I might pick ones that look, if I'm finding them easy, because you don't need to do all 50 of them, right? But I might be like, ooh, look, which ones look kind of juicy? 17, 13, 48, 50, 40. Like I'd be looking for ones that look goofy, right? And I'd be seeing if I could find those ones. Are we good? Yeah, okay, cool. Okay.
I've gone to it's a dense one.
I think I will let Tyler teach you about oxidizing and reducing agents. Okay. You can do that at home over the weekend. So we are now moving on to 6.1D, which is on page 10.
Yeah.
Would you guys like to see a redox reaction?
Sure.
Okay. I'll be right back. Actually, okay. So I have here this beaker full of copper waste. I was trying to go crystals and purify it, but I never quite got far enough. So what I'm going to do is I'm going to try and hack out some of the crystal. And we don't ever want to put copper ion down the drain because it's really toxic for plants. So I'm going to try and chip this out.
Aerosol.
Do you know what charge this copper is? 2+, because copper 2 is blue. Okay.
What happened?
Okay. Who wants to start? Excellent. Just do that. Watch out. Okay. We're just going to see if we can get as much of this dissolved as possible. Maybe maybe I need to add a little more water. Now you'll notice there's some impurity in there, which is why it's looking a little cloudy, but we are getting that typical blue color. Okay. Okay, we're gonna try now to see what happens if we put some aluminum in there. Because we've got copper. What is the charge of copper here? 2+. Do you guys want to come up and see? You could shut that thing so you don't get blinded. It's just the little black slider at the front, very front. There we go. Thank you. So yeah, if you want to come up, some of you can come behind. That way everyone can see. If you're in the front, you can crouch down. You can come behind me. It's okay. Okay, so here we're going to just toss this in and see what happens. And maybe nothing will happen at first, because this isn't a proper, I haven't made a proper concentration of solution and stuff. Going? Maybe we need to wait a little while.
Yeah, should we cook it?
Huh?
If we warm it up on a hot plate.
Maybe. I'm sure that would make it go faster. I've actually never done it with copper sulfate. I've only ever done it with copper chloride. Maybe that's the problem. That could be the problem. Okay, I'm going to go get some other copper solution, and we're going to try this again.
The reaction watered it down the reactor before it's going to rust.
It's gonna blow up.
What are you saying? I'm dead ass with it. We need another person. Alvin, can you help us not make this a swastika?
Oh yeah. No, I wasn't, bro.
I would support Nazi ego.
I thought we both came from.
There we go.
Boy, you pro Nazism. That doesn't really.
Yo, what?
What?
Wait, did you just say pro-Nazism is a reasonable thing?
That's
The exact opposite of what you just said. Oh, it's floating.
Now, where did I put my stirring rod? There it is.
Okay. That's kind of a crazy take.
Yeah, and then you notice that. I'm getting kicked out of.
Oh, there we go. This one's going.
Ooh. Oh, I see. Oxidation.
This is way more. Oh, what are we getting on
Why
there?
are you smoking?
It's not rust. Rust is iron oxide.
Copper.
We are getting copper metal. So copper is coming out of solution and turning into copper 0. Yes, and what's happening to the aluminum?
It's reacting with the chlorine.
Is the aluminum still like aluminum foily?
No.
No. Is it disintegrating?
Yes.
Yes, that's because it's stopping being aluminum 0, which is a nice solid, and it is losing electrons and becoming aluminum 3+. Those electrons that it is losing are going to the copper 2+. Yes. And so now we're getting the aluminum solid is going away, and the copper. So apparently copper sulfate doesn't work. I don't know why, but at any rate, that's what happens. And if you keep adding aluminum foil long enough, you will get solid copper, which can then be disposed of through, like, we've got a district person who comes around and collects things, right?
Where do
So
they put the stuff?
what's that?
Once they collect it, where do they?
Honestly, I don't know when they collect it anymore because the guy who did it retired last year. So I don't know who's coming to get it now.
No one's going.
There may just be a huge bucket of copper in the back room, you know, like 30 years from now, they'll be like, what is this?
Can you melt down
Anywho.
the copper?
So there we go.
We can make like
Okay, and I'll throw a little bit more in there and we'll see how it eventually turns, like, so it's not blue at all anymore. All the copper too will get used up. All right.
That's actually kind of cool. I'm not even gonna lie. That's
Okay, sit down. Hi. My what?
jacket is on your.
I mean, jacket is on my cookie. Oh dear. There we go.
Are you sure? What do you think you're awesome? Okay. What happens?
Okay, you need some paper that is not your book. You need some paper that is not your book. Please write the products and balance.
I agree.
We're doing the formula equation right now. Once you've done the formula equation, if you would like to do the complete ionic equation and the net ionic equation, you can go for that too. What type of reaction is this? It's a single replacement, so go ahead and single replace. Yes, please balance.
Oh yeah, I just did that. Oh, okay.
Okay, are we good? Are you getting what I'm getting? Excellent. And now what we're going to do is we're going to say, this is a little thing, it's a little trick that we do in redox equations. It's not something we would do in other equations because it doesn't make any sense. We are going to take our copper and we're going to isolate that part of the reaction. That part of the reaction is called a half reaction because copper 2+ turning into copper 0 is half of the redox reaction. What would the other half reaction be? It would be the aluminum solid with a 0 charge turning into aluminum 3+. And that's the other half reaction. So any redox equation can be split into 2 half reactions. Are we familiar with the term redox? Okay, if you are not familiar with the term redox, make sure that you get a copy of 6.1a and watch the Tyler DeWitt video because it goes over what redox means. Redox means oxidation reduction reaction. Now, I don't know why we always call it oxidation reduction reaction, or we call it redox. I don't know why, if we call it redox, why we don't call it a reduction oxidation reaction, but we don't. It's just weird. But we're good? Okay. Any redox reaction, pen stopped working. There we go. Can be split into 2 half reactions. Okay, so for example, we are going to take our 3Cu 2+ aqueous going to our 3Cu solid. However, what should I do with that equation? Yes? Well, hold on. There's something I need to do before that. I need to take out the 3, okay? We need to take out the 3. All right, so we're going to rewrite that as Cu 2+ aqueous goes to Cu solid. Now, before we do anything else, I would like to ask you, what is the oxidation number of copper here on this side? 2 plus. What is the oxidation number of copper on this side? 0. So did this oxidation number get bigger or did it get smaller? It got smaller. The oxidation number got smaller. In other words, i.e., the oxidation number got reduced. So what type of half reaction is this? Is this an oxidation half reaction or is this a reduction half reaction? It's super hard. It's a reduction because the oxidation number got reduced. Before we go on, is this equation balanced? Tell your partner, do you think that equation is balanced?
In this equation, we go through the
I feel like maybe I should make a seating plan. That's what I do with my grade 9s when they're too noisy. I make a seating plan. Are we into that? No, okay. So reactions, including half reactions, must be balanced in terms of not only the number of atoms, but also in terms of the charge. So the reaction up here is balanced in terms of number of atoms, but is it balanced in terms of charge? No. What could we add to make it balanced? I know, Elliot, just put your hand down. I know, Nathan, just put your hand down. Rigel. Yes, we can absolutely add 2 electrons to this side, and now we have a 2 minus and a 2 plus. What does 2 minus and 2 plus equal? 0, which equals the charge on the other side, 0. Okay, so that would be our balanced reduction half reaction. Now, we learned that it was a reduction half reaction because the charge, the oxidation number, got reduced. There is another way you can tell by looking at this reaction to tell that it is reduction. How else could you tell that this is a reduction half reaction? Discuss. The electrons are in the reactants, the electrons are going in. Therefore, are we gaining electrons or losing electrons? Therefore, we are gaining electrons, and therefore that would be reduction because Leo the lion says grr. Gaining electrons is reduction. Grr. Or you could do oil rig. I don't know. I only put that up there because Tyler had it. It doesn't do anything for me. I like having a little lion. It's more fun, but you know. Okay, what is our other? Could you please write and balance our other half reaction from that overall redox reaction?
Regarding like the logic, I
Yeah.
didn't get a key for 5.
You didn't get a key for this one, 5.6? Yeah.
C, yeah.
Where's 5.7C? 5.6C? Let me find it.
Yeah.
Okay.
Yeah.
Oh, that's what you rather
Yeah. No, I don't think it because both your eyes are doing it.
Oh, they're all like, but like,
Yeah.
so like,
Or you can go on Teams and I'll.
I'm looking for the
So I'll see.
It'll work. It'll work.
Yeah.
that makes me good, but I assume there's no state on the electron, right?
There's no what?
No state, like liquid.
No, they don't have a stake, no.
You got mad. So they put you all in.
Now, obviously, since the other half reaction was reduction, this one must be oxidation. Prove to me in 2 ways that this is oxidation.
Electrons oxidate. How are you gonna break that? Because it's like products, you like walls, you know. Oh no, everyone yes.
What are they doing? I'm not looking for. All I'm hearing is yeah.
Okay, so hopefully everybody, I am going to come up with a seating plan. I'm not even kidding. It's ridiculous. I'm going to put like noisy people with quiet people. Okay, losing electrons is Oxidation, that's one way. What's another way that we can do it?
Oxidation number.
We can do oxidation number. What is the oxidation number of Al? And what is the oxidation number of Al3 plus? Plus 3. And so we have the oxidation number has increased, which is oxidation. Okie dokie. Now, if you are given two half reactions, you can actually put them back together into a full reaction. And let's just do that right now. Was that okay? Yeah? Okay. Let's take our two half reactions. Two half reactions make one overall redox reaction. So if I were to throw you this half reaction, and this half reaction, now the trick is when you have two half reactions, you need to make the electrons going in equal to the electrons going out. So what we're going to do is we're going to multiply these reactions. What would we multiply the first reaction by? 2. That's going to give us 6 electrons, yes?
Yeah.
And what are we going to multiply the second reaction by? 3. Okay, and I'm going to rewrite these reactions so I have 2 Al now goes to 2 Al3 plus 6 electrons. And now I also have 3 times 2 is 6 electrons plus Cu2 plus gives, 3 Cu2 plus. Go away, Andrew. You're distracting them.
Oh, my bad.
Yeah. It's not your fault. They're eminently destructible. Eminently destructible? I can never remember which is which. I always say the wrong one, but I know what they mean. Imminent means like it's just about to happen, so that's not the one. Eminently means like I'm really bad at defining things. Like I know what it means, but I can't think of how to define it, which is really stupid. But anyway, if you're eminently something, you're like really, really that way. Like, I don't know. Rigel? Of course. What? 5.4. Is it on Teams? 5.4. No. Now what we're going to do is we're going to add these two reactions together. Boom, boom. Okay, and now we have 2 Al plus, and then we've run out of reactants from the top half reaction, 3 Cu2 plus. gives us, and then we go back to our top reaction, 2Al 3 plus 3 CuS, and now we've made it full circle back to our original net ionic equation. Yes? So sometimes you will be given a redox reaction and you'll have to split it into half reactions. And sometimes you'll have to bring them back together. Very often, you'll be given an unbalanced redox reaction. You'll have to split it into half reactions, balance the half reactions, and then put them back together once they've been balanced. In a situation like this, that's too fancy. You can just figure it out. But there will be situations where you're like, you know, if you tried to balance it by inspection, you could be here from now till Tuesday. Do you guys ever remember coming across any balancing reactions where you're like, crap, I don't know how to do that? Any of those? If you were in my class, probably not, because I didn't give them to you, because I'm like, why should you learn this now and balance by inspection when you'll be learning redox next year and it'll all become easy? So if you had me, you probably didn't learn any, but if you had someone else for something else, maybe grade 10, you might have seen some crazy ones. Anyway, that's what we've got there. Is good? Okay. Are there any questions about your quiz tomorrow?
No.
No. Okay, yes. We have a shorter block tomorrow, so there's no way I can do all of 5.4, 5.5, 5.6, and 5.7. So let's go to our upcoming quizzes and tests. 5.5 and 5.6 and other titration stuff. You know the one that I handed out that was stapled that said other titration stuff? Friday, December 13th, 14th, 15th, 15th, 15th. 15th. There we go. Is good? Not five. Does it say 5.4? No, I don't have to. We don't have time to do that many questions. But is 5.4 on Tuesday's test? Yes. Is 5.7 on Tuesday's test? Yes. So does that mean that you're just not going to study them at all? No. Okay, good. Does everybody have the overall review package for acid base 2?
Yes.
Yes. Very good. Yes. There could be. I mean, you're expected to know the titration words, right? You should know primary standards. You should know equivalence point, endpoint, standardized solution. Okay, excellent.
I looked it up.